Let's talk about memory. No, not the where did my keys go and what was the name of my first grade teacher kind of memory. And no, I don't know the answer to either of those questions right at this moment. It might take me a bit. No, today we are talking about high bandwidth memory, specifically dynamic random access memory or DRAM. You know, the kind of memory that makes the world go round these days. There is a bigger and bigger demand for DRAM for a lot of different applications today. And nowhere is it more important than in AI systems and data centers, where low latency and low power reign supreme. So, have you heard about the innovative new DRAM solution called the Cube? Oh, my friends, it is super cool. And that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Omar Ma from Winbond and I explore how we can power the AI revolution with Cube. We also investigate how AI model parameters compare with DRAM density, why green DRAM can be a great solution for edge AI applications, and how the cube can be scaled for implementation in a wide variety of applications, including AI acceleration, AR/VR, smart cameras, and more. And before we get started, don't forget to click that link. There you can find even more information about this topic from Winbon. Hi, Omar. Thank you so much for joining me.
Thank you, Amelia. It's my pleasure to join the talk today.
Excellent. I'm glad you're here. Okay, so we're talking about how we can power the AI revolution with Cube. But before we get started, Omar, set the stage for us. We're looking at a big growth in DRAM. What specific segments are you seeing the biggest growth in?
I think before we start, let me try to explain what the cube is, and everybody will be on the same page. So the cube actually is the initial, stands for customized ultra bandwidth element. So from this, the full name, you can tell there's no standard cube. It's most likely is a customized device. So each of them will be tailor-made device. And the Winbond is capable to craft memory device based on customers' needs. That's why we call it Cube. So basically on the chart, we are seeing like year over year DRAM demand trend. So DRAM demand in all the application actually increases years over years. From this DRAM big growth trend, we can easily find that almost every segment needs more and more DRAM, no matter it's a mobile device, PC, whatever it is. So everything, the DRAM demand goes up. So I believe the biggest driving force is AI. And also the compound annual growth from the right-hand side and the bottom of the table, you will see almost everything like mobile device is about 9%, PC is about 5%, and the consumer electronics is about 6%. And I think we are very familiar with those traditional applications. For example, when we buy a new phone or a new laptop, the maker, when they show their specification to us, they will tell us how much DRAM is used for this device. And it's very easily to feel the increase every time when you buy the device. And the trend also apply to other segment, but it is not easy to be discovered. For example, data center. If you are not in the data center industry, you probably will not notice how big the DRAM demand change. So for example, DRAM actually for data center is really amazing. From the chart, you can see it is hard to imagine that only in that region, the overall DRAM usage in terms of density will be almost the same or even bigger than the rest of all the application. When you see the color, the brown one is data center. When we talk about, for example, 2028, the brown bar is probably bigger or higher than the rest of the application. So that's what I mean. The data center actually, from density wise, it's very big. And you probably know why cause or drive this kind of increase. It's HBM technology. But actually, except the data center, there are two segments have a highest growth rate, which is I highlight here. One is IoT, and the other is automotive. The IoT is about 30%, and the automotive is about 28%. So basically, these two are number one and number two perspective. And so basically, these two segments are super hunger for memory. So however, in the most of the cases, they don't need super high density, and they are not high performance driven application. So therefore, HBM, what we just talked about for the data center, may not be a good choice for them. Besides, HBM has a high cost and a high power consumption. So use HBM will become a burden for those kind of application. So our cube comes to help them. So of course, they can use general DRAM, but if the user wants their product stands out of their competitor, I think our cube product will be a good choice.
So, Omar, within AI applications specifically, walk me through the different memory types and how they compare when it comes to power and performance.
So basically, as you can see, different application has different hardware configuration. Fastest speed or biggest density memory may not be always a good choice. So we can categorize into three types of application system, which is MCU-based, microcontroller-based, MPU-based, microprocessor-based, and multi-core application processor-based. We just try to simplify how to categorize the application by the processor or SoC from SoC point of view. Okay, so for a MCU base, they will use embedded OS most likely, such as RTOS, real-time OS, and they are used for some control operation, which means a very simple control application. So memory bandwidth and the memory density is not so important in the past. And some of them don't even need any external memory because, as you know, MCU, there always has an embedded SRAM inside. So probably internal SRAM is good enough. And maybe in some cases, low density pseudo SRAM type of the thing or hyper RAM, 2 megahertz and below works fine. However, when we talk about AI, we found more and more MCU-based system integrates very simple AI function, which means their DRAM requirement increasing. For example, if you have a voice recognition or basic image processing feature, and then they will need more DRAM or more memory to be able to processing all those data, not only just simple control on and off things. And for the MPU base, usually they already need a much bigger density DRAM or memory. And it requires light OS, such as Linux, and they are higher performance processor. So definitely they need DRAM. And it handles more complicated jobs. For example, in the slide, you can see from communication-wise, it's probably applied to 3G, 4G, or a little bit 5G application, and the high-speed Wi-Fi, and the higher resolution image processing, and or even video processing. So you can notice that DRAM bandwidth requirement become higher. And just like MCU, when customer need more AI features, it will become even DRAM hungry. And if we go to the AP multiple core application processor, DRAM density and speed reaches another level because they are going to handle very complex tasks or even multitasking. The OS will be very rich OS, for example, Android or Apple iOS or something like that, and plus building AI models. So generally speaking, if any AI feature is developed, no matter how simple it is, in what kind of system, you will need more DRAM or memory to help to process all those models, parameters, or the contents when you enable the AI function.
So, Omar, let's take a closer look at a cloud server memory system.
So cloud application is very important. However, like we discussed in the beginning, Winbond is more interested in some applications which requires memory, but not super high performance, super high density, but lower power consumption and the medium to low density. And most importantly, the bandwidth. Those applications still need bandwidth. And I have to say, on the cloud side, HBM serve those applications very well. So it looks like HBM is born for those applications. But how about the other applications, such as those IoT device, our router at home, smart speaker, or even smart TV? Once they enable AI, the memory requirement also increases, just like we talked about previously. So on this chart, the X direction is the performance, which is a TOPS, and it's usually how we calculate the AI performance. And the Y-axis is the power. So we try to use the memory density and the memory bandwidth to describe our focus. If you remember in the beginning, we talked about HBM, which is for a very high-end and a high-performance scenario. So in this chart, it belongs to the far right-hand side segment. And we are more interested to serve and contribute to the first two areas, which is the endpoint AIoT and also the edge AI segment. So like endpoint AIoT, their performance is usually around 50 TOPS, around that range. And the power consumption, maybe it's about 10 watts. I mean, this is a system power consumption. It's about 10 watt and below. Their AI model is some light inference job. And certain edge AI application, they can handle powerful inference so that they are hungry for memory as well. And for those usage case, unit cost will be very critical. For example, the router, you are not able to, because the cost is there. So you are not able to adopt the HBM. So the total cost will be much higher, so nobody will buy your router. And also, this is a very big market, or say the volume is huge. So if they cannot find a good DRAM solution, I will recommend to consider our Cube family. And you may notice that we spend some time, actually, we spend a couple slides to address the application by either processor or memory density or bandwidth perspective. So the reason is actually our Cube technology is highly bounded with processor design. So we welcome all the customer, but if any customer who wants to develop SoC or have special DRAM requirement, it's even better by using Cube technology.
So, Omar, talk to me about AI model parameters and how it compares with DRAM density.
So this chart is for helping people to understand what the cube's position is and how cube can be used. So let me roughly explain this chart. So there are three colors, I mean the line or dot. The first one is gold or light brown. This is for generative AI development trend. And the second one is gray line is for AI hardware development trend. And the last one is the red one is used to show edge AI development trend. So all the dots, of course, in the same color as the line, all the dots indicates either AI model or hardware technology. We can see from about 2018 to 2019, the first generative AI was released. So we called it the GPT-1. And it is about to handle, at that time, 100 million parameters. If you see the Excel, it's about 100 million parameters. And in about a year later, the GPT-2 was out, and the AI parameters was increased to 2 to 3 billion parameters. If I read the chart correctly, it's about 2 to 3 or maybe 4, something like that. 1 year later, the GPT-3 can handle about 200 plus billion parameters. And then it took about another 2 to 2.5 years. The GPT 3.5 came out, and it is what we see today called the ChatGPT. Let us talk about the AI hardware. So the hardware we just talked about is the gray line. So basically, for example, it was TPU plus HBM2 in the beginning in 2018 or 2019. The DRAM or memory usage or requirement is about 32 gigabyte. And when we see the 2020 timeframe, it was AI 100 with HBM2, 80 gigabyte. And the 2022 H100, it's a HBM3, reaches 96 gigabyte. So when we talk about the model parameter and the DRAM density, you can see when you need to process higher and higher parameters, then the DRAM density keep growing. And now we are talking about more than 200 gigabyte. If you see the right-hand side, there's a B20 something, and the DRAM requirement is almost 200 gigabyte. So it exactly shows how AI hungers for memory in generative AI segment. For the other type of AI, like we said, is our focus. So if we go to the bottom portion, the red line is another type of AI model, such as YOLO, SAM, or Llama. They can be used for image detection, text-based analysis, or content generation jobs. These are easily to be seen or to be adopted in IoT devices or endpoint or automotive application. When the memory density reach to 8 gigabyte and above, the performance larger than 40 TOPS. Our Cube technology kicks in. I think you can see on the right-hand side of the red color portion when we try to introduce our Cube. As we mentioned previously, Cube is highly bounded with SoC. So from the picture, you can see it is actually a stacking structure. So which means memory stacked with SoC. Normally, SoC is on the top die, and the Cube is a button unit. And SoC connect to Cube die through either advanced package technology, hybrid bonding, or microbump. And all the signal pass through TSV in our Cube die and connect to the package substrate. And everything we just talked about is actually in one package, SoC stacked with DRAM, Cube, and in one package. Since the Cube is customized unit, people can design different DRAM architecture that fits their SoC the best. If single die density is not big enough, we are able to do multiple die stacking, just like the right hand. If the single cube is not big enough, we can do multiple die stacking. And because DRAM cell is capacitor based, then the Cube has another advantage. Cube die can also put some silicon capacitor on it as a coupling capacitors, and it can help signal integrity or even power performance. So you will see some difference between HBM and the Cube. We are actually trying to fill the segment which HBM cannot serve.
Okay, so Omar, an important aspect of Cube is how it scales as well. So talk to me about that aspect.
This is another good chart to explain how we position Cube. So as we mentioned previously, HBM is for very high densities, 30, 40, or even a couple hundred gigabyte type of density with very high performance. It is very good for generative AI or ChatGPT application, which is on the far right-hand side. But for the general DRAM, if you can see in this chart, we are very familiar like DDR4, DDR5, low power DDR4, low power DDR5, etc. So they are good for middle density. Roughly a component level is about 1 gigabyte to 16 gigabyte. And also they can provide medium bandwidth. I believe it is still very popular for the most of the consumer application and the mobile device. But if a customer need higher bandwidth, but not high density, that is what our Cube's chance. So like we show here on the upper left corner, before Winbond Cube, there's actually no solution for it at all. So because it is a customized device, Cube-Lite can be designed to have hundreds or even thousands of I/O, which means you can run your device at a very low frequency so that user can reach. But based on that, multiple I/O, thousands of I/O, low frequency times these two together, you can reach similar bandwidth as HBM. For example, if clock rate is 200 megahertz with the double data rate technology, it will be 500 megabit per second per pin or per I/O. And say if Cube designs a 1000 I/O, the total bandwidth will be 62.5 gigabyte. So this is a very high bandwidth DRAM. Actually, I think it's higher than the most of the traditional DRAM. Besides, lower frequency means lower heat and the lower power consumption. And we can stack our cube die to achieve even higher density if single die is not big enough. And currently, our technology can achieve 4-die stack. And in the future, we are seeing our target is about 8-die stack and even further. So that is Cube's position.
Omar, what about green power DRAM? What does that look like for these kinds of edge AI applications?
Okay, so green power DRAM is not just a slogan. Everybody knows right now we need power saving. Everything needs to be green, lower and lower power. However, we don't want to sacrifice the performance. But in Winbond, actually, green power reflects what we are doing at this moment. So there are actually two things. One is from device itself, and two is from the DRAM manufacturing. Like we mentioned previously, Cube used tons of I/O to achieve high bandwidth by running at a very low frequency. So the power consumption will be low, so that the heat will be also very low. So let me use a 1 gigabyte Cube-Lite as an example. And you can see the middle picture on this chart. So basically, it offers the same bandwidth as low power DDR4X. However, the power consumption is about 30% lower than the same density of low power DDR4X. So I believe this represents how good the Cube power saving feature is. And besides, we also talk about DRAM manufacturing. Winbond is also working on green manufacturing. So in the future, our goal is our factory will use all the recycled power, which is a green power completely for all the products which manufacture in Winbond. So we are doing our best helping carbon neutral and make Earth greener. So as you know, we are a memory company. So except Cube, we also offer all kinds of a traditional DRAM. When we design, we also consider low power consumption. So even those legacy DRAM such as SDRAM, low power DDR2, so on and so forth. So as we just mentioned, different system has different application and their target market. So I believe user can always find right solution from us.
All right. So, Omar, can you give me some more details about Cube?
Of course. So currently, I believe we talk about Cube for a while, and currently in our company, there are actually two types of Cube products. One is Cube, which is a fully customized product, and the other we call it Cube-Lite, and you can see on this chart. It is a finished design. So what's the difference? And basically both products are mainly for SoC vendor, like we described in the previous slide. We bounded with SoC vendor closely. Those vendor or those customer who has new design but cannot find a suitable DRAM solution, so they can consider either Cube or Cube-Lite. The first Cube is customized, so each design is unique. So we are not able to share lots of detail at this moment because each one is unique. But what we can do is we can talk about some Cube-Lite. In this slide, we are talking about a 1 gigabit density Cube-Lite DRAM with a 128 I/O And if the clock rate runs at 250 megahertz with DDR feature, the total bandwidth is about 8 gigabyte. So it's about the same as 1 gigabit low power DDR4X running at 2133 megahertz by 16 IO device. So if we compare clock rate, 250 megahertz versus 2133 megahertz, Cube-Lite will have better power consumption, of course, and also signal integrity performance will be better because it's hard to control 2 gigahertz and it's easier to control 250. So it can be a good option for AI, ISP, or wearable device with embedded AI features. So from the picture at the bottom, our Cube-Lite does not have to be on the bottom die. It also can be on the top die, depending on customer's design. But the thing is, SoC pad design need to match our Cube-Lite because this is a finished design. It's not fully customized. So because Cube uses, like we just mentioned, hybrid bonding or microbond technology to be able to attach a Cube die on top or bottom of the SoC. Because of that, there's no memory PHY in the Cube design. So therefore, it is very similar to inner connection when you design a chip, which means the loading, IO loading, will be extremely low. So that is some advantage and more detail about our Cube technology.
Omar, what would you like my audience to take away from today's Chalk Talk?
Sure. Today, we just talk about DRAM's future trend and the AI market situation. And because AI changes our world rapidly, memory becomes more and more important. And the demand also increased dramatically. So Cube's position actually is very clear. It's the best solution for customer who needs high bandwidth, but also needs low power. And they don't really need a very high density, but still a decent density. So that's where Cube stands. Currently, we offer two types of Cube, Cube and the Cube-Lite. From the name, you can tell Cube is more higher density, more powerful, and Cube-Lite is light version of a Cube. So each has its segment to fit in. So in edge computing category, user who use LLM, which is one of the AI model, or SLM model for specific inference or reasoning purpose, Cube could be better choice because when application needs to deal with high tokens per second, which is a TPS, and high bandwidth is very important. Besides, Cube can be 3D stacking or 2.5D structure depending on SoC structure or the design or density requirement. So that's for Cube. And for CNN model, convolutional neural network usage case, although JEDEC DRAM can still perform very well, I believe, at this moment. But for certain cases, sticking for ultra low power, I think Cube-Lite is another solution, just like we compared Cube-Lite versus low power DDR4X. So the power consumption can be much lower. Especially this is very important for battery power device. I think that's the takeaway we want to share with all the audience. So basically, depending on what kind of a design you are working on, if it's a richer OS, higher, a little bit performance hungry, you can choose Cube. On the other hand, if it's a light usage or light OS, you can choose Cube-Lite. And especially if the power consumption is very important, the Cube-Lite is a good solution for you. So this is all I want to share with you and hope this helps.
Thank you so much for joining me, Omar.
Likewise. Thank you, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Winbond. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE.